Hungarian Academy of Sciences and the Technical University of Budapest. And he will tell us about near-critical SLE6 and the tail in Cardy's formula.
Okay, sorry for being late. The lunch was too good. Okay, it's the last day of a nice conference. So I want to. So don't worry. Everything I will prove will be very simple. So I will prove two simple things. But I also want to explain some less simple questions to you. And also the simple things I think they are nice. So I hope you will enjoy them. I can already tell you what the two results are. So I will be talking about near-critical percolation, near-critical SLE6. And it's kind of obvious. So you take, okay, I will define it carefully, but it's slightly supercritical percolation. So let's say if you take the usual SLE6 picture that is black on this boundary and white on this boundary, and the interface is going. And if black has a little bit of higher probability, then the SLE6 is going a little bit that direction. Okay, so the Loevner driving process should be a submartingale in that direction, right? Kind of obvious that this is what we expect. So this is one thing I'm going to prove for you, that it is a submartingale. And I will also tell you we have a conjecture how the drift term should look like in this Loevner process. So I will tell you the conjecture that we have. So this is kind of partly joined with Christoph Garban and Odette Schramm. And I will also tell you about the tail in near-critical Cardy's formula. That is, if you take a 1-by-1 box and take a near-critical percolation at level lambda, large lambda, then the probability that you have a left-right crossing is close to 1, right? Question, how close is it is to 1? So the probability that it's not crossed is 1 minus exponential of minus lambda to the 4/3. Okay, that's the result that I'm going to prove. So if you need to catch a train like Gregory needs, he already knows what the results are. Okay, so I need to give a little bit of introduction, even though, so Laure has done most of the work this morning. So I just very briefly will say a few things that she hasn't mentioned. So I will be looking at critical percolation, but I want to view it. I want to watch the evolution of the connectivity of the graph of the lattice as I'm raising p from 0 to 1, especially close to the critical parameter. So I will have these uniform labels on the edges, or actually, well, I will be mostly taking side percolation on the triangular lattice. So these would be uniform labels on the vertices, and percolation at level p is the collection of the p clusters. So the clusters whose given by the connected components of this graph with labels at most p, right? So the usual monotone coupling of percolation. Okay, and we know that at 1/2 there is a phase transition. Okay, and we know Smirnov's theorem. So just the notation. So critical side percolation on delta 1/n. So that will be the triangular lattice with mesh size 1/n. And I will be talking about quads. So this is as I think Laure drew it. It's a simply connected domain with piecewise smooth boundary and 4 marked points. So a generalized rectangle, like this. Okay, and we know that crossing probabilities are conformally invariant in the limit, right? So the probability that you have a left-right crossing inside the quad has a limit, and it's conformally invariant. And the value in anything like that is conformally equivalent to a rectangle of a certain shape, and the probability of the left-right crossing in this rectangle is called Cardy's formula. Okay, and we have SLE6. Now, okay, also Laure mentioned that there is an issue of, if you want to talk about the scaling limit of percolation, for instance, you need to say what is the topology in which you are taking the scaling limit. And since we are interested in the macroscopic connectivity structure of percolation, we want some topology that is encoding this macroscopic connectivity. And so one possibility is this quad crossing topology of Schramm and Smirnov. Another possibility is SLE6, so all the interfaces between black and white clusters. So this conformal loop ensemble. Eisenman had a suggestion is that the collection of all the paths that go inside clusters, there is the exploration tree of Scott. So there are different possibilities for this topology. Obviously, they are all the same, right? They contain the same data. Okay. Now, if you actually want to prove, then well, I don't know. I don't recommend. It's kind of some directions are known that this topology is stronger than that topology, but typically people take the topology that is they like the most and that is the most comfortable to work with for that problem. And for percolation, these quad crossings are so well, there is no quad now, but anyway, so quad crossings are so natural that somehow we take the quad crossing topology. But it's known, so for instance, from the work of Kami and Newman saying that there's a unique scaling limit given by SLE6. From this, it follows that there is also a unique scaling limit in the quad crossing topology. So for instance, that direction works. So there is a scaling limit in this Schramm-Smirnov topology. Okay, and now I want to look at the near critical window. So there are two ways of saying this. One is that if I look at the left-right, the probability of a left-right crossing in a given quad, let's say the unit square with mesh n, then the probability goes from 0 to 1, right? And it's exactly 1/2 at 1/2. And the critical window, this tau delta n, is the window where the probability becomes from delta, it becomes 1 minus delta. And we know that it converges to 0 with n. Okay. I will tell you in a second how. The dual picture is what. So this is like what combinatorialists usually look at, and physicists like to look at the correlation length. Right. So if you fix your p, then how big a box do you have to take so that you already see that your p is supercritical, so that your crossing has probability already beyond 1 minus delta. Right, and the two functions are this tau, right? So how much you have to go beyond PC, and the L of P. These are inverses of each other. These two functions. Okay, and for percolation, we know what this critical window is already from Kasten 87. Is that the near critical window for percolation is given by the expected number of pivotal points at criticality. So the size of this tau n is 1 over the expected number of pivotals, which is n to the minus 3/4. Okay, right? So Lohr also explained that pivotal means that pivotal for the left-right crossing, which is the same as having an alternating forearm event from that point. Right? If this is white, then you have a white crossing, left-right, and if it's black, then you have a top-bottom black crossing. And right, from SLE calculations, we know that with this alpha 4 probability, so the probability that a site has this alternating forearm event to distance n, that's alpha 4n, and that's n to the minus 5/4, and there are n squared, around n squared sites inside in the bulk of the domain. So this gives n to the 3/4, and you in expectation, and you can prove that there aren't many pivotals close to the boundary. So really, the boundary doesn't play a big role in the expectation. It's the bulk. So it's n to the 3/4. And okay, and why does that give the near critical window? Well, so R of n will be always the 1 over the expected number of pivotals at criticality, this n to the minus 3/4. So if you go beyond PC by much more than R of n, then in expectation you have opened many sites that were pivotal in the critical picture. So this is only in expectation, but you can also prove that it's true in probability. So first of all, there are little issues that you have to be careful with. With positive probability, there are no pivotals at all at criticality. If you have 2 disjoint crossings, with positive probability this happens, and you don't have pivotals. However, if you have pivotals, then you have the number of pivotals is comparable to the expectation. That's already good. And so if you start raising P above PC, then even if you didn't have pivotals at the beginning, eventually you will have pivotals, and you will have many pivotals, and you will switch them. So you can prove that with large probability you have switched pivotals, and at that point you have the crossing. So with large probability you will have the crossing. So so the critical window is at most this R of n. Now there's a question: can the window be smaller than R of n? And a priori it's possible. So you are raising P, you are getting out of criticality, and this R of n was the expected number of pivotals at criticality. So maybe as you are moving out of stationarity, out of criticality, maybe new pivotals arrive. And maybe at some point there are much more pivotals than at criticality, and hence they are easier to switch on. Hence you get a left-right crossing earlier than R of n. Right? This might be possible. And this little picture illustrates that that new pivotals do appear. So when, like in this picture, at criticality, there is no pivotal for red left-right crossing. Right? Whatever you change, if you change one site, nothing changes. You still have you still have this blue dual crossing that blocks you. However, if you change this one site, then suddenly this has also become pivotal. I mean, this has become pivotal, and there are many such sites actually around. So suddenly, new pivotals appear. However, there's a calculation, this stability calculation that Lohr mentioned, that so although new pivotals do appear, but not too many, so that they won't actually switch on. So if a pivotal appears because of switching something, that pivotal, the new pivotals won't be switched. Okay, so somehow they don't really matter, only the pivotals at criticality that really matter. So you can prove that. So actually the proof of Kasten was different. He used the differential inequalities to prove the same statement. And So this Kesten stability is that multi-arm probabilities, like the 4-arm, the pivotality probability, stays comparable inside this entire R of n regime around PC. Hence, you don't get more pivotals, and everything is changing at the same time. So you really need this R of n. You need to move out above PC with this R of n to see changes. Hence, this is the critical window. Okay, this is the this is the proof of the critical window. Okay, so there's a digression. Just let me say this. So just to appreciate better that this Kesten stability holds for percolation, it doesn't hold for FK easing. So so it doesn't hold for any Q bigger than 1, but we understand the Q equals 2 case much more, of course. So so the expected number of pivotals, so in FK easing, at criticality is n to the 13 over 24, but the critical window is only 1 over n. So 1 over n is much smaller than n to the minus 13 over 24. So really, changes in the near critical regime are faster than what you would expect from the expected number of pivotals at criticality. And this is the reason for this is that in any monotone coupling, so as when you are raising P and C, so it's not obvious what the monotone coupling is for FKPQ, but there is for Q larger than 1. You can define a monotone coupling. So as when you are raising P, you see the edges appearing in FKPQ. And pivotals are actually more likely to get opened, much more likely than other ones. And it's even worse. There are atoms in this coupling. In any coupling, it seems there are atoms. So there are edges who have the same labels. So when you raise P, and suddenly 100 edges appear. And these edges can organize between themselves where they go. And really, it seems they want to create longer connections. So really, the near critical changes are faster than what you would expect from the critical number of pivotals. Okay, so it's not a triviality that this holds. The stability holds for percolation. Okay, and then the theorem that Laure mentioned is that so we take percolation at PC plus lambda times R of n, where lambda is a fixed number between minus infinity and infinity, and then we let n go to infinity. Then for any fixed lambda, we actually get a near critical percolation scaling limit in the quad crossing topology. So this is NC, near critical ensemble scaling limit. I call it an ensemble because I also want to look at it as lambda is changing. So they are all coupled together. And in fact, as you are changing lambda, it is Markovian in lambda, which is not obvious, and it's conformally covariant. If the domain is changed by a conformal map phi, then the time is scaled locally by the derivative to the 3/4. And the reason for the 3/4 is very simple. If you increase the domain, then you will have more pivotals there. And the pivotality exponent was 3/4. Hence and if you have more pivotals, then time is changing faster, right? The little change in lambda actually, if you have more pivotals, then then they are more likely to be opened. So you need this scaling in time. Okay, and I have to say a little bit about this. So the main point of this construction is not just it's not completely just an existence result. The main point is that we construct this from critical percolation, from the scaling limit of critical percolation. And that's a good thing because, for instance, with this you can prove conformal covariance. Right? So you need to use some knowledge of conformal invariance to understand this conformal covariance. Okay, and there are two main things that you have to do. One is that okay, we know that this dynamics, as you are changing lambda, depends on opening the pivotals. Okay, when I'm saying opening the pivotals, I'm kind of loosely. I'm a little bit loose here, so I think of a point is epsilon pivotal or epsilon important if it's pivotal to distance epsilon, right? And you have to look at all the pivotals that are pivotal to some macroscopic distance. Okay, but in the scaling limit, there are no sites anymore, so you don't know how to. So what is a pivotal point in the scaling limit when you have only the crossings of quads? So the main, so one main step is to prove that from the quad crossing configuration, you can actually detect how many pivotals, how many epsilon pivotals you have at different places in the domain. So there is this local time-like measure on pivotal points, and from macroscopic information from the quad crossing scaling limit, you can actually tell that here you have more pivotals, here you have less pivotals, and so on. So there is this pivotal measure on epsilon pivotal measure supported on epsilon pivotal points on the scaling limit of epsilon pivotal on the set of epsilon pivotal points, and this measure is measurable with respect to the quad crossing configuration scaling limit. Okay, so this is one thing you have to do, and the other is this stability that when you are changing lambda, you want to say that it's enough to follow initial, so lambda equals 0 macroscopic pivotals, how they change, and when you open them, then clusters merge. But so it's enough to follow what's happening to them, and you don't need to. It's not. So it doesn't happen that a point was important to some very small microscopic distance, and it becomes macroscopic during the dynamics, and then you would need to know what's happening with that. No, it's enough to know the lambda equals 0 slice, the initial slice, and use independent randomness. So Poisson clocks, a Poisson point process of switches with intensity measure given by these pivotal measures, and they tell you where the clusters merge. So that's the picture that we how we understand this near critical scaling limit. Okay, so now I want to understand the exploration interface in this near critical percolation. So okay, so this is an interface between black and white in critical. Now, if you want to understand you start raising the level. So you start merging clusters. So if you want to see what's happening to this SLE 6, then of course you also need to know how the clusters look around this curve. So you also need the clusters surrounding them, or surrounding it. And then there are these pivotals who ring. So right, they used to be white, and now they turn black. Okay, so these are the ones who ring, and they deroute the interface. Okay, so careful simulation, as you can see. Okay, so this new path is, of course, to the right of the old blue path. Now, okay, so really this scaling, this near critical scaling limit that we have built is really different from the critical. You would need to prove that, right? That it's not just. It is different from the critical percolation scaling limit. Why is that? So it's actually singular the massive, it's usually called massive if you're not exactly at criticality. It's kind of introducing mass in the system. So in these near critical scaling limits, for any lambda, they are actually singular with respect to the lambda equals 0, and also with respect to each other. Okay, for the full quad crossing scaling limit, this is easy to see. So there is this little lemma that if you take the left-right crossing in a u by u square, the probability of that at level lambda is half. So when lambda is positive, it's 1/2 plus some c lambda times u to the 3/4, because the number of pivotals is kind of u to the 3/4. So with positive probability, that's the expected number, and you have, with positive probability, you have at least one. Actually, with positive probability, you have many of them comparable to the expectation, and with positive probability, you switch one of them during the limit, during this, so at this level lambda. So really the probability that you have switched a pivotal is comparable to u to the 3/4. That's so the usual scaling. Okay, and once you have this, divide the 0, 1 square into small 1 over k by 1 over k squares, and and look at the number of small squares that are small 1 over k by 1 over k squares that are crossed, and look at the event that the number of such squares is larger than half plus half the density of what you would expect from this bound. Okay, so because I took c lambda over 2 here, while the probability was c lambda there, the probability that this is happening is close to 1. Right? I mean, I had a drift larger than what I took here. So in the lambda level, this event has a probability close to 1. However, at criticality, in the 0 measure, it has probability close to 0, because this drift is larger than what you get from normal fluctuation. Right? The square root of k squared is only k, and k to the 5/4 is larger than k. So you don't expect this to see in criticality. Okay, so hence you let k go to infinity, and you prove that the quad crossing limit is singular. Okay, and to say that this one exploration path, this one near critical SLE6 is singular with respect to normal SLE6 is harder because you have less information, but it is true. Pierre Nolan and Wendelin Werner, they proved the singularity of the exploration interface by a similar but harder argument. There you have to say that the interface meets about k to the 7/4 small squares, and in each of these small squares you have this k to the -3/4 drift to the right. So altogether, by visiting k to the 7/4, right, that's the dimension of the interface. So altogether you collect a drift k by multiplying these two together. So there's a resulting drift k, which is larger than the normal fluctuation square root of this thing. Okay, so sort of that's the idea of their proof. Okay, there's a remark that singularity. So there are several ways of defining near critical SLEs. There might not be a unique way. I will remark that more later. But somehow for natural near critical models, you expect that for k bigger than 4, kappa bigger than 4, you have singularity, and for kappa less than 4, you have absolute continuity. And somehow the reason is that for kappa bigger than 4, you have many pivotals, and when you are changing them, it feels a lot. Okay, now, so of course you expect, as I mentioned at the beginning, for the Loebner driving function WT, you expect it to be something like the normal SLE6 plus a monotone positive drift term for lambda positive. So why should it be square root of 6 times dBt here, because when you zoom in spatially, is the same as moving lambda closer to 0, right? The whole thing is scaling covariant. So it's kind of when you look very close, it looks just like ordinary critical interface. So, for instance, the dimension of near critical SLE6 is the same as critical SLE6. So you cannot change things like dimension. Okay, and as I said, you expect a positive drift. Now the problem with proving this is that so you know, what does this WT measure? It's the harmonic measure looked from infinity of the left side of the curve minus the right side. And you know, typically, this is the picture. Typically, so of course the left side of the green curve is larger. You know, has become larger than before, but it's not always the case. So, like if you just glue this little thing here, you haven't changed the left side of the curve at all, but you increase the right side of the curve. Okay, right? So it may happen that your random walk, Brownian motion started from infinity, comes here, and it didn't, before it wasn't here, it didn't touch here and came here, but now it's swallowed there, right? So the harmonic measure now is bigger on the right. Right? So if you want to prove sub-martingality, then you need to do it on the average. It's not true pointwise. So in the natural coupling, the new WT is not always larger than the old WT. And so here is the trick. Right. So the expectation of WT is the expected difference between harmonic measure of left side and right side. So let's measure this difference. Instead of letting a Brownian motion from infinity, I will let a percolation interface from infinity. Now you have to be careful what that means, because right, if you take a chordal SLE6 from here to there, then and you reverse it, right, it will have infinitely many touch points on both sides immediately, right? So if you want to ask, do you hit the left boundary of this curve, right? The left boundary also includes this entire Dobrushin half. So do you hit the left boundary or the right boundary first? The question doesn't make sense because you immediately hit both sides. So you want to take an excursion. So you condition the interface to leave, I don't know, distance or capacity or something epsilon, and then you rescale it. So you get a non-probability measure. It's some scale invariant measure, and with that you measure if you hit the left or the right. Now there's a very strange trick that so this trick is from an old email of Oded that we managed to dig out a few months ago with Christoph, and there was this argument that made no sense. And we looked at it, tried to make sense of it, still no, and at some point, well, if you do this and you reverse, then it actually works. Okay, there is no mention of this in the email, probably Oded knew, but because the rest of the email doesn't make sense without this trick, but I didn't see this trick before. So somehow we found out that this is what you have to do. So although this interface that I'm measuring is plus on the left and minus on the right, okay, well, I'm taking also, well, looked from above, I take plus on the left and minus on the right. So this is the interface that I'm emanating from infinity. And so what are these two curves now? There is this blue critical one. And the way I sample the near critical interface is simply by, so I switch only the pivotals that I meet. Right? So for a while there are no pivotals, no pivotals have been changed, but here I don't know if it's visible, there was a blue minus, but now it's a green plus. So this pivotal has switched and it made the interface go left. And here there was another blue minus that turned into green plus, so we keep on that side, right? So we do these changes along, so we have these changes along the near critical interface, but nowhere else. And this is what I sampled. And the rest of this will be just critical critical percolation. And this is important because if I want to measure the harmonic measure of this site, then it's important that this interface be critical. Right? I need the conformal invariance to make the connection with the with harmonic measure. Okay, so this is what I do. And now, miraculously, if you look at all the possibilities that can happen, so let's say this interface, maybe it touched first, so the first case, A case is that it first touches the blue interface on the plus side. Well, then it has to come this way, and there is no way to hit. So also it must have hit the green interface on the, well, on the, it also must, right? I mean, once you detour here, you cannot hit the, yes, so eventually we'll hit it. We'll hit it here. So we will also hit it on the plus side. And okay, so look at all these possibilities. So you have to be a little bit careful with the changes because they change where the interfaces go, but everything is right. You will always hit. So if you hit the original interface on the plus side, you will also hit the green interface on the plus side. Hence, in this coupling, the difference between the probabilities of hitting on the left is always larger for gamma 2, for the green one. Okay, so here I fixed gamma 1, I fixed gamma 2, and omega is the percolation configuration. Okay, and now if you average over everything, you get that the average left side of gamma 2 is larger than the average left side of gamma 1. Now, when you look at it first, this is like a pointwise inequality. So didn't we prove what I thought was wrong? That always pointwise the left side, right? That is, I told you that it's not true that the green interface always has a larger left side, plus side than the previous one. But no, it doesn't, because right, to actually get the harmonic measure of the interface gamma 1, I have to average out over not just omega, but also over gamma 2. So I condition on gamma 1 and average over everything else. So this is the harmonic measure of the difference between the harmonic measures of gamma 1. And this is the harmonic measure for gamma 2. And here the averaging is everything but gamma 1, and here the averaging is everything but gamma 2. There is no way from here to get to here, right? I'm not doing the right averaging. So somehow this coupling between gamma 1 and gamma 2 is interfering with the with calculating the harmonic measure. So it's a strange thing, but so this is the proof that it's a submartingale.
What do you do with the time parameter? You said nothing about the parameterization of the curve. You need to compare them at the same time somehow.
Yes. You have to do something.
Because you could always try to extend the green until it's to the left from the point of view of harmonic measure, which will happen by fluctuation, and then it seems to go in the wrong direction. If the blue part is very small and the green part goes all the way to the left.
I don't think that's possible, but I mean to. Oh yes. That's a good point. I guess you have to. Okay, I have a vague answer, but I have to think about it. So.
Okay, I'll do it again.
So, but yeah, that's a good point. Okay. Okay. So what? Okay. So what could be the form of this AT? So now this is completely conjectural. I mean, you know, this could be made sense of, but it seems to be hard. Some hard work is needed. So, so when you take you have this, you have the interface and you let it grow a little bit. Okay, and then you take the Loebner chain. So gamma t is the tip, and you look at a row neighborhood of the tip. This is what is written here. For percolation, the expected the critical percolation, the expected number of pivotals is okay, and at mesh size 1 over n is rho times n r of this to the minus 1. Right, this is the expected number of pivotals. So at level lambda, when you change, when you go from PC to PC plus lambda times r of n, the expected number of pivotals you have changed is lambda times rho to the 3/4. Okay, roughly. You know, on the discrete level, there's a plus little o of 1. So this is the expected change in the crossing probability. Okay, which kind of means that your expected exit position from this little ball after time dt should be about it's moved to the right with this degree. So the expected change in the degree of the exit position from standard is this lambda to the rho to the 3/4. Okay, now under the Loebner map, when this radius becomes roughly, you know, it was a small radius, so it becomes roughly another ball of radius some rho prime. Right, when this was time dt, then this is roughly square root of dt. This is how the Loebner chain works. So what do we? So and we have this this expected degree in the change. So the drift to the right should be this lambda to the rho to the 3/4 times this rho prime, the radius here, which is kind of right. The rho was how much gamma has changed, right? I moved with gamma the rho, so there's d gamma t to the 3/4 power, and dt square root is the, as I told you, the rho prime. So dat should be something like, you know, the change in you know, the drift you accumulated in time dt should be this. Okay, so you get an equation. dwt is this plus this. It's severely self-interacting, right? You have the gamma t that WT defines for you inside this drift. So it looks like a hard equation. Now, one question is that if you wanted to see if actually this has a chance to make sense, this SDE. So if you wanted to take take the integral form and approximate it, then a possible question, if you have the d gammas to some power d1 and the dt's to some power d2, and you have this Riemann approximating sum, for what d1 and d2 do you have a chance for this to converge? For SLE6 or something that looks like SLE6 locally. Okay. Now, okay, I'm not sure I want to go into the details, but so there are derivative estimates that you assume that the near critical SLE has the same derivative exponents as but you want to see that when you map then around the tip how much the distortion is. So the derivative of the Löwner map raised to the d1 power, how that behaves in expectation. So when you do these calculations, this is some quadratic thing. There is a square and a square root, and if you want this thing to converge, you get an equation for d1 and d2. So there is d1 and d2 need to satisfy this for this to converge. Okay, this is heuristics because I don't know if near critical SLE6 has the same derivative exponents. Okay, on the other hand, you can also, so this was suggested by Bertrand after a talk I gave when he saw this crazy SDE, that also the dimension count should be fine. Right, so we have the P is PC plus lambda times n to the minus 3/4. P is density; it doesn't have any length. But lambda to the n to the minus 3/4, n is a length thing. So lambda has is a length to the needs to be length to the 3/4 to have this right. And so if you look at this thing, the dimension count should be fine. You get this other equation. Now these two equations together, they have two solutions. One is d1, d2 is 3/4, 1/2, the one we had, and the other is 7/4 and 0. So you can also try to look at this equation with 7/4 and 0 and see if it has any meaning in percolation. Is this a different near critical? You get a different near critical SLE6, or what's happening? We don't know. Okay, so okay, so the obvious questions are about these massive limits. So one is that prove the previous formula, prove uniqueness for that self-interacting SDE. Now there's a question: is it useful? Okay, you have a formula. Is it useful for anything? Right, SLE6 can be used to calculate Cardy's formula. Can this horrible thing be used to calculate near critical Cardy's formula? So one thing we vaguely thought of is maybe not exactly the formula, but maybe the tail of the crossing. When you take large lambda, what is the probability? How does that behave for large lambda? Maybe that you can study for this SDE. Okay, okay, and I will tell you in a few seconds. There's a much easier way to actually find that tail. Okay, another question is that you have for the near critical interface, you have locality, and you have rotation and translation invariance, and you have the Markovian property. Do these characterize near critical interface, up to the choice of lambda? Okay, does d1, d2 lambda, this thing, does it describe anything meaningful? somehow I imagine it should be related to the natural parameterization of SLE6 because it's gamma to the d gamma to the 7/4 power, but okay, I don't know. And this is just okay. Makarov and Smirnov have a ICMP announcement of massive harmonic observables, and we just heard a talk about massive harmonic things from Cedric. Is this? Can you? Anyway, is there any connection between these two approaches? Okay, is there a near critical scaling limit for FK random cluster models? We have no clue. Okay, and in general, how many massive versions of SLE kappa could there be? We don't know. I know that Stas told me that he has been bugging physicists with this question, that he thinks that there could be more than one or more than two, but everyone tells him that he's stupid. Everyone knows what the near critical perturbations are, and but Stas hasn't managed to figure out why only those are the meaningful near critical perturbations. So it's yes, it's not clear that we know all near critical perturbations. Okay, and so in 2 minutes. So the tail of the crossing probability. So in any given quad, we can look at this, right at level lambda, what is the probability of crossing, of left-right crossing in the quad Q. Okay, now this formula is conformally covariant, as we know. So in particular, it's scale covariant. So if you multiply lambda by rho, it's the same as multiplying the domain by rho to the 4/3, right? Okay, so we will use this. And already from Kasten, we know that if you take lambda close to -infinity, then the probability of a crossing goes to 0. And if you take lambda, right, this is just saying that the window is really what we are looking at. If you take lambda to +infinity, then the crossing is converging to 1. And the question, how fast does it converge to 0 and to 1? And the answer is e to the minus lambda to the 4/3. And so I was actually reminded of this question by Alberg and Steiff, who have a paper that studies in general what kind of scaling limits you can have for threshold functions of monotone Boolean functions. And they actually prove that anything, you give any distribution function, you can get that as a scaling limit. But they also wanted to know, for specific nice Boolean functions, what are the limits, and for instance, what are the possible tail behaviors. So here it's lambda to the 4/3, and the proof. No, sorry. Okay, the other question I really like. So I had another motivation for this question. You can also do dynamical percolation. So instead of changing everything, you're changing lambda. Instead of opening the sites, you could just change them back and forth between black and white. So you keep it stationary criticality, at criticality. So this is called dynamical percolation. And just the same proof as for near critical percolation. It's actually harder for the dynamical than for near critical. Also, dynamical percolation has a scaling limit. So you have a Markov process on SLE6. Pieces get glued and get separated. And you can look at this question. If you are running it for time t, what is the probability that you don't have a left-right crossing for all this time t? Right? So this should go to 0, but how fast does it go to 0? And so this has a limit as n goes to infinity. And this is this gt. And with Alan Hammond and Elhanan Mossel, we managed to prove that it's at least exponential. And at most, so it's smaller than any polynomial. These are kind of, so there is some input from Fourier analysis and stuff, but it's kind of general. So spectral computations are dynamical FKG inequality is kind of generic Markov chain arguments. We managed to get this, but we don't know what the truth is, and I really would like to know. This is just a simulation. So this is the near critical tail. This after I take the log. So this is super, right? It's super exponential e to the minus t to the 4/3. So this is the function t to the 4/3, and this is the simulation for this dynamical thing. So it looks sub-exponential, right? But I don't know what that is. And it's kind of, so this is kind of the first instance that I know that near critical scaling limit and dynamical scaling limit really behave quantitatively or qualitatively, anyway, really behave differently. So I like this. So even though we don't know what this is, but we know that it's bigger than exponential. Okay, and just one sentence about the proof for the tail is is that it's very similar to Hugo Duminil-Copin's proof that if you take the percolation Wolf shape, so what is that? In supercritical percolation, you condition the cluster of the origin to be big but finite. Okay, and this is hard. You get some limit shape. You know, if you condition the volume to be n squared, then you divide the radius by n, you get a limit shape. And it was a folklore conjecture that as P goes down to PC, because of the rotational invariance at PC, the Wolf shape should become circular. Right? It's very natural, but the problem with it's not obvious because there's an interchange of limits. Right? In the Wolf shape, first you let n, the mesh, go to, so n go to infinity, and then P go to PC, while the rotation invariance that we know is you look at PC, you take n go to infinity, then we have rotation invariance, and then what? Then you take a shape, which is scale invariance. Anyway, it's so there's a non-trivial interchange of limits. And what Hugo noticed is that the existence of the dynamical percolation scaling limit, the near critical ensemble scaling limit, gives you a good way to interpolate between, you know, to make this change of limits. So in particular, you know, if you fix any lambda, let's say lambda minus 1, then the probability that, let's say you take take two boxes very far from each other. What is the probability that they are crossed? Okay, it's exponentially small in that distance. Okay, this is just like supercritical or subcritical percolation. Okay, but this is in the near critical regime. So, but this is just you prove the same way as, you know, Peyer's argument and stuff like that. But you do this in the near critical, and then you just apply the scale covariance, and you get the result. Kind of, if you think a little bit about it, it's not hard. So somehow seeing the supercritical picture already at the limit, which is scale covariant, is a very nice thing that can be used to understand many things. Okay, I stop. Thank you.
Questions or comments?
Can you look at near criticality in the ON formulation?
In the
ON formulation. By changing the length finalization.
where we haven't looked. Okay, I don't know.
So the massive guy with the 740, where you say related to natural parameterization, I mean, do you have a more precise
No.
statement?
No, I have no clue.
That you're going to, could this one be still absolutely continuous with respect to the?
I don't know. How do you study such a thing? I don't know.
I mean, if you know the natural parameterization is Hölder or something with respect to
Yes. Yes.
maybe you can check whether the I mean just the
Yes. On the.
anyway, it's just a question.
Yeah, I don't think it should be absolutely continuous. I mean, it should be singular. I mean, if it exists, I don't.
There's
Thank